Morning. Welcome to my video tutorial. This is Sudharani, Head of the Department of Computer Science, Madurai Sivagasi Nadars, Pioneer Meenakshi Women's College. In this video tutorial, I am going to teach you the topic Arithmetic Building Blocks from the course 7BCEE2A, that is Digital Principles and Computer Organization. So the agenda for today is we are going to discuss about what is an arithmetic building block. Then we are going to discuss about the building blocks half adder, full adder and controlled inverter. Come, let's dive into the topic. The first agenda is what is an arithmetic building block. An arithmetic circuit is a set of gates with a separate set of inputs for each number that has to be processed. The gates are connected so as to carry out an arithmetic action, and the outputs of the gate circuit are the digits of the result. That is, the digits of the result of an addition, subtraction, multiplication or division operation. So, the three basic circuits are half adder, full adder and controlled inverter. The first arithmetic building block I am going to teach you is the half adder. Now let's see what is a half adder. When we add two binary numbers, we start with the least significant column, then we'll proceed with the next higher order column, and this will be continued until we reach the most significant column. So we need to add two bits with the possibility of a carry. The circuit used for this is called a half adder. So the block diagram of a half adder can be represented like this, which is presented in figure 1. So half adder, it has two inputs, say A and B. These are the two inputs of a half adder, and the outputs are S and C out, where S represents the sum of the two inputs A and B, and C out represents the carry produced out of addition of A and B. The next is the truth table of a half adder. So as you know, the half adder has two inputs which are represented as A and B, and it produces two outputs, say sum and a carry. So when the two inputs are 0, the sum output will also be 0 and carry will also be 0. When input A is a 0 and input B is a 1, the sum output will be 1 and carry will be 0. When A is 1 and B is a 0, then also sum output will be 1 and carry will be 0. If both the inputs are 1, then sum will be 0 with a carry of 1. Now, we have framed the truth table of a half adder. The next is we need to frame the Boolean expression. Then the Boolean expression may be simplified to arrive at an optimized logical circuit, and finally the logical circuit will be constructed. So let's start with the Karnaugh map for sum. So here this is the Karnaugh map for sum, and here we have two ones, say 1 and this one. This one represents AB complement and this one corresponds to A complement B. Since they cannot even form a pair, they should be considered for the logical expression as it is. So sum is equal to A complement and B, or A and B complement. And as we know, this is the logical expression that corresponds to the output of a two input exclusive OR gate. So we can implement the sum with an exclusive OR gate with two inputs. Consider the Karnaugh map for the carry. Here we have only 1, 1, which is nothing but A and B. So from the truth table we can understand that the carry output corresponds to the output of the AND gate. So the Boolean expression for carry will be A and B. So carry may be implemented with an AND gate. So now we have framed the Karnaugh map for the outputs sum and carry. Now let us construct the logical circuit of a half adder. Slides. The output of the exclusive OR gate is the sum and the output of the AND gate is the carry. So the inputs A and B are given as input to the exclusive OR gates, and the two inputs are given as input to the AND gate. So output of the exclusive OR gate is the sum and output of the AND gate represents the carry, and this is the logical circuit of a half adder. The next is the operation that corresponds to the half adder. From the truth table itself, we can understand that the operation of a half adder is similar to that of the binary addition. With respect to binary addition, there are only 4 rules. That is, when a 0 added with 0, the result will be 0 and carry will be 0. When one input is a 0 and the second input is a 1, then sum will be 1 and it does not produce any carry. When one input is a 1 and the second input is a 0, then also the sum will be 1 and carry will be 0. When both the inputs are 1, the output will be 1, 0, where the 0 represents the sum and 1 the carry. So we can understand that the operation of a half adder is similar to that of the binary addition, or we can perform the binary addition with the half adder. Now let us consider the applications of a half adder. A half adder is used in arithmetic logic unit of computer processors to add binary bits. It is used to realize full adder circuit. A half adder is used in calculators. and it is also used to calculate addresses and tables. Now, what is the conclusion about a half adder? From the above discussion, we can conclude that half adders are one of the basic arithmetic circuits used in different electronic devices to perform addition of two binary digits. But the major drawback of a half adder is that it cannot add the carry obtained from the addition of the previous stage. So to overcome this drawback, full adders are used in electronic systems. So the next arithmetic building block I am going to teach you is the full adder. A full adder, which is meant for adding higher order columns, or I can say that for adding the binary digits that correspond to higher order columns, we use full adder. So full adder is a logical circuit which can add 3 bits at a time. The 2 bits are the binary digits to be added, and the third bit is the carry from the lower column. It's a logical circuit which has 3 inputs and 2 outputs. Or in other words, a combinational circuit that can add 2 binary digits and a carry bit and produces a sum bit and a carry as output is known as a full adder. In other words, a combinational circuit which is designed to add 3 binary digits and produces 2 outputs, say sum and a carry, is known as a full adder. Thus, a full adder circuit adds 3 binary digits where 2 are the inputs and 1 is the carry forwarded from the previous addition, and it produces 2 outputs, say sum and a carry. The next is the block diagram of a full adder. So here A, B and C in represents the 3 inputs to a full adder, and S represents the sum output of the full adder, and C out represents the carry from the full adder. The next is truth table of a full adder. So we have 3 inputs to a full adder. So we need, or we have 8 combinations. When all the inputs are 0, then sum will be 0 and carry will also be 0. When A is 0, B is 0 and C in is a 1, then sum will be 0 and carry will be sum will be 1 and carry will be 0. When A is 0, B is 1 and C in is also a 0, then also there is only 1 in the input, so sum will be 1 and carry will be 0. If A is a 0 and both B and C in are 1, then there are 2 ones in the input, so sum will be 0 with a carry of 1. When A is a 1 and both B and C in are 0, then we have only 1 in the input, so sum will be 0 and sum will be 1 and carry will be 0. If A is 1, B is 0 and C in is also a 1, then we have 2 inputs as 1, so sum is 0 and carry is a 1. When A and B both are 1 and C in is a 0, then we have 2 ones in the input, so sum is 0 and carry is 1. When all the inputs are 1, then sum and carry both will be 1. So this is the truth table of a full adder, and we have to frame the logical expression for sum and carry. Then let's simplify the expression so that we'll be getting the optimized logical circuit. So let's see the Karnaugh map of the sum output. Here also we have 4 ones as we have seen in the truth table, but since then there is no possibility of forming a pair, so we have to consider the ones as it is, and very well the Boolean expression is A exclusive or B exclusive or C in. So the sum output can be very well implemented using a 3 input exclusive OR gate. The next is the Karnaugh map that corresponds to the carry. Here we can form pairs. 3 pairs can be formed. So the Boolean expression for C out is equal to AB or BC in or C in A. So the logical circuit that results for the full adder will be, this is a sum is implemented using a 3 input exclusive OR gate, and carry output is implemented using the expression AB or BC or AC. So this is how this will be the logical circuit of a full adder. Now what are the advantages of a full adder? A full adder provides facility to add the carry from the previous stage. The next advantage is the power consumed by the full adder is relatively easy as compared to half adder. Full adder can be easily converted into a half adder just by adding a NOT gate in the circuit. And full adder performs operations at higher speed. The next is about the applications of a full adder. Full adders are used in arithmetic logic units of CPUs of computers. They are also used in calculators. Full adders helps in carrying out multiplication of binary numbers. Full adders are also used to realize digital circuits like multiplexers. Then the next application of a full adder is they are used to generate memory addresses. Full adders are also used in generation of program counterpoints. Full adders are also used in graphical processing unit. The conclusion: full adders play an important role in many digital electronic circuits because a full adder can be used to realize several other digital circuits. So till now we have discussed about 2 building blocks, say half adder and full adder. The next building block is the controlled inverter. A controlled inverter, it is an arithmetic circuit which is going to transmit the input as it is, or it is going to transmit the ones complement of the input. So to control this, we have control signal, say inverter. If the control signal invert A is low, then the circuit transmits the input to the output. So there is no change in the input and the input is available at the output. When this control signal invert is high, the circuit will transmit the ones complement of the input. So the logical circuit that corresponds to the controlled inverter is shown. We have a control signal, say inverter, and we have 8-bit input represented as A0 to A7, and the output is represented with Y0 to Y7. So in this example, we are considering the 8-bit input. So the invert input is connected to the main building block used here is the exclusive OR gate. The control signal invert is given as input to all the exclusive OR gates. The second input of the exclusive OR gate is the inputs. So output of the exclusive OR gate will be either, if we consider the first exclusive OR gate, it will be A0 or A0 complement. If we consider the second exclusive OR gate, the output will be either A1 or A1 complement. This is true for the remaining inputs. So output Y will be A if control signal invert is equal to 0. Output Y will be equal to A complement if invert is equal to 1. This is what the control inverter is. Let us consider an example. If the input is 0, 1, 1, 0, 1, 1, 1, 0 and the control signal invert is equal to 0, then output will be, as I already said, the input will be available at the output with no change. So output will be 0, 1, 1, 0, 1, 1, 1, 0. If input signal is a 1, then the output will be the ones complement of the input. So in this example, the output will be 1, 0, 0, 1, 0, 0, 0, 1. I think you can understand the operation of a controlled inverter. If the control signal invert is equal to 0, the input is available at the output with no change. If invert signal is 1, then the ones complement of the input will be available at the output. In what way the controlled inverter will be helpful in an arithmetic circuit? So during subtraction, the subtraction operation will be performed by taking 2's complement of the subtrahend. Then the complemented subtrahend will be added to the minus n to obtain the answer. And 2's complement is nothing but 1's complement plus 1. With the controlled inverter, we can produce the 1's complement, and it will be very helpful during a subtraction operation. That is the purpose of a controlled inverter. So in this video tutorial, I have taught you the basic building blocks, say half adder, full adder and controlled inverter. Hope you could have a better understanding of the 3 building blocks. Thank you. Thanks for watching my video tutorial. We'll meet in the next tutorial. Thank you.